have Brian Henning from a PFL talking about a non-perturbative construction of the S matrix. We thank you again, Brian, for accepting our invitation, and please take it away.
Well, thank you very much, Joao, and the rest of the group there for inviting me out. I'm very happy to be here presenting a work done in collaboration with Hitoshi Murayama, Francesco Reaver, Jed Thompson, and Matt Walters that we're all very happy about. It came out about a little bit more than a month ago. I want to pause for a second and mention Jed here. He is graduating and applying for postdocs this year, and he's just an absolutely stellar person. So keep your eyes out. It's on the market. Great. So here's a rough outline. There's probably more material in here than we have time for, and I would much prefer you guys to interrupt me and ask questions along the way, so please don't hesitate. But we'll go through a fair amount of sort of motivating the problem at hand, and then we'll get to the results. But let's show something interesting from the beginning. First of all, this is sort of my dream. We have in the real world a field theory which we know exists, strong QCD, but we don't know how to describe it quantitatively fully. So it's a very wild theory. As you can see around about a GeV, the spectrum contains many different resonances. There's a ton going on here. And the ultimate sort of dream in my mind is to be able to come up with some sort of numerical method of producing these plots from first principles. We're not there yet. We've just started on our way. And let me give you the punchline of the talk. So shown here is a cross-section for a strongly coupled field theory in 3 dimensions. It's fully non-perturbative in the calculation, and we're going to provide a recipe for computing amplitudes in general non-perturbatively. With there's some extensions that will be needed for full generality, and we'll get to that at the end. But what really goes into this is a set of energy eigenstates, which are obtained from some sort of method. I will be using Hamiltonian truncation, but that will play sort of a little bit in the background here. So any way that you can sort of obtain energy eigenstates, you can use this method. And it can access the full complex plane, which is a very nice feature of it. And it can go beyond the elastic region, which is what's capable for the lattice, and into the full inelastic region. So as you can also see from this plot, this is order 1% residuals. And this is on a laptop in a few seconds. We didn't try and push this as far as we could. It was already pretty good from the get-go. So now that we know where the talk will basically end, let's go through why we're doing this. Like I said, QCD is sort of a wild theory. It's super rich. It's a multi-scale problem. There's intricate phase structure, so we don't know what happens at high density and high temperatures. And there are various phase transitions that could be relevant for the early universe or, crossovers. And it'd be very nice to be able to explore this. I want to point out that it's not just, so it's sort of well known that, of course, QCD, the coupling constant blows up. We can't calculate in a certain regime. So a lot of times I think it's often thought that it's a primarily quantitative problem, which of course it is, but there's also qualitative features about QCD that we don't understand. So even the most basic observable, which is the spectrum, what are the particles of the theory? There are puzzles here. So shown here are some now discovered tetraquark and pentaquark states at the LHC. And these have no normal explanation within inside QCD. So we don't know how these arise. They've been extremely well discovered. So I like this around 2014. So this is around when the Higgs was discovered, and we all fussed about 5 sigma for the discovery. And here we are, tetraquarks are already sitting at 14 sigma 10 years ago. And we need to figure out how to explain them. There are many regimes where strong coupling comes into play. So at the LHC, what happens predominantly the 2 protons come and they pass each other, or they do some sort of forward type of scattering. So this dominates the cross-section at high energies. And what's happening, so by sort of passing each other, they can exchange a lot of soft radiation. about order GeV. And so you're in this regime where GeV exchange is happening, so it should be somewhat strongly coupled. And what happens is that it sort of exchanges a whole tower of resonances at once, and that sort of dominates the cross section. This is the Pomeron. And while we do know how to obtain a Pomeron-like object out of QCD, it's not the Pomeron that's observed an experiment. Namely, the Pomeron sort of controls the growth of the cross-section as S to a power. And out of QCD, you can calculate a power here, but it's not the observed power. So we don't know how to do it. And so it's modeled phenomenologically at the LHC. Now, LHC is full of jets happening all over the place. And what really happens during hadronization? That's a puzzle that's still left to be unraveled. I want to point out that in the past couple of years, there's been some interesting progress on looking at different types of observables in scattering events. Sort of came from motivation actually out of conformal field theory and conformal collider physics. But the idea is to sort of what does a detector do? Well, it's just a sort of measuring energy deposition, and that's asymptotically removed from the interaction point. And so they're studying so-called energy correlators, which are integrals of the stress tensor along a null line, and just really measuring that energy is flowing in some direction. And by looking at these correlators, they can actually observe a lot of really interesting phenomena. So shown here is sort of in the bottom, an angle measured between a 2-point correlator. And as it passes through this is also sort of measuring a regime of energy scale. As it passes through the hadronization scale, you get very qualitatively different features on the side. And so they can actually now measure these objects, and they're sort of well-defined theoretically. So at the end of the talk, I'll mention again that I think that this would be an interesting avenue to try and study non-perturbatively. Now, of course, there's been a ton of sophisticated machinery developed to study strongly coupled physics in QCD. A lot of it is built around effective field theories. I won't get into the detail here, but it's an amazing feat to be able to isolate the relevant degrees of freedom, parameterize them, and then sort of measure them. But what goes into it is sort of an undetermined set of coefficients. And these can either be measured by experiment or computed with the lattice. And it would also be very nice to have other options. So perhaps the best well-known, and for very good reasons, approach to non-perturbative physics is through lattice Monte Carlo methods. So this is formulated, it's important to realize that it's formulated in Euclidean space. It's a path integral approach. And the Monte Carlo means they're doing some sort of numerical sampling of the path integral measure and essentially directly computing the correlation function from the path integral. Because it's Euclidean, that means time is not real time there. So they don't actually have access immediately to dynamics. So they don't have access to scattering phenomena, for example. That's not fully true. What they can do is there's actually some very interesting and nice methods to extract the elastic amplitude, which you can do out of sort of finite volume spectra. So sort of measuring how, like, when you have two particles together and you pull them apart and how that energy spectrum changes, you can actually extract the scattering phase in the elastic region for this. This is the Lucier method. So that's what's sort of generating these plots here on the right. There's also been some very interesting recent progress on trying to use the lattice to study correlation functions, and then out of the correlation function extract the amplitude. Technically, this is an ill-posed inverse problem, but they are making progress on it. So it's an interesting place to look at. But also fundamentally, the lattice, if you just like, we should just use the lattice for everything, we can get past the analytic continuation and all this. Well, it's formulated to QFTs, which have a lattice formulation. And famously, our standard model does not. So the lattice doesn't know how to handle chiral gauge theories or chiral fermions. So we need an alternative to the lattice. So I like to refer to the alternative that we use in this paper as the dumbest idea, which might actually work. And that's how I've historically referred to it. Now we actually see that it will work, so that's quite nice. The question is sort of how well will it work then? But the idea is that you imagine that you have some UV theory, which you know, so you know it's Hamiltonian and you know its spectrum, the eigenstates and their eigenvalues. And then you take this UV theory and you add a potential to it, some deformation of it. We're going to focus on relevant deformations in this work. Then you have essentially just an H naught plus V. What can I do? I have the energy eigenstates from H naught. I can compute their matrix elements, diagonalize the matrix, and then this will approximate the true spectrum. So this is the broad idea of Hamiltonian truncation. So again, the idea is sort of you have an H naught and a V, and you're sort of looking at a subsector of the full Hamiltonian matrix. And what goes into this sort of choice of, so the states that you'll use for this H trunk is a choice of a Hilbert space inside the full Hilbert space. So this is a tricky problem because the Hilbert space grows exponentially in size. So on some level, there's an argument to be made for, well, the only way that you'll ever be able to solve this problem is to actually use quantum simulation, which can get past the exponential size because it's actually a quantum system. However, we believe that if you're clever, we know that physics, we know some things about physics and we can input that data. So if you choose a smart basis ahead of time, you might be able to approximate the physics that you want to. Another important aspect to realize of this is that normally this matrix in the field theory is a continuous matrix. So it's labeled by continuous numbers. In order to put this on a computer numerically, of course, you need to discretize the system some way. So you're essentially putting the QFT in a box. The box can be quite literally, you've compactified space to a finite volume, or in our case, the actual method we use, we technically work at infinite volume, and the box is a little bit more subtle what shows up, but there's always a box. So what can truncation do? Again, its basic output is you're diagonalizing a Hamiltonian. So you're going to get the spectrum info immediately. And from that spectral info, you can compute things like matrix elements, which then allows you to go on and compute correlation functions like 2-point functions. So historically, these have been some of the first successes in the use of Hamiltonian truncation. So it actually works fantastically in 1+1 dimensions. In the past 10 years or so, it's really seen a revival, and we've seen very interesting work where you can, through study of correlation functions, see things like resonances appearing, closings of gaps in the Ising model. And there's been a lot of work on systematic renormalization so that you can get better convergence with the system. All this is being done on the laptop. And so it's quite interesting work, but physics in 1+1 is a bit of a playground, and it's not always immediately generalizable to higher dimensions. So when you go to higher dimensions, it's harder, but it's still doable. So one of the big things about it is just by increasing, adding an extra dimension, you're going to require a sort of bigger set. The Hilbert space gets bigger, and therefore you'll kind of need a bigger basis to approximate the physics that you want. However, and also going into, for example, 3D or 4D, we have many less exact results to compare to. But in a way that's sort of another blessing because it's uncharted territory. So for example, in 2+1 dimensions, most of the couplings that you'd want to study, like a phi to the fourth, the Yukawa coupling, or gauge theories, are all relevant deformations, meaning they all flow to strong coupling in the IR. And for most of these theories, we don't actually know what happens. So shown here in some plots, I just want to point out some of the things that you can study. So like in this bottom right, they're studying a 2-point function of an operator near criticality in the 3D Ising model. And so near criticality, correlation functions behave like power laws, of course. And what you're seeing on this plot, so it's quite literally on the x-axis, the argument is m times x, so how far you are. And as the theory sort of flows near the critical point, you get this power law behavior here from which they can extract the critical exponent. Now, there are better methods for obtaining the critical exponents at this point, but it's quite nice to see this happening. So spectral information and two-point functions are all very useful and super cool objects to study, but we were motivated to go after what probably the first object that many of us learned about in our QFT courses, or that was emphasized as hugely important, which is scattering in the S matrix. So I'm gonna pause for a moment just in case there are questions. All right, so how do we compute the S matrix then? So the fundamental question is, you're given a set of eigenstates. We use truncation, but you can imagine them being given from some other place. And if you have such a set of eigenstates, how do you compute the S matrix? So in a sense, let's go through sort of why this is what you might naively try at first and why it's a hard problem. So of course, the S matrix is defined as the overlap of in and out states. So in a sense, the problem is trivial if you've been handed the in and out states. Okay, so your first guess might be, let's look for the in and out states in the spectrum. Well, how exactly is the output from your computer related to them? The problem is there is no real notion of them. So if you think in finite volume, for example, there is no notion of asymptotic infinity. So there's no formal definition of asymptotic states. Ultimately, and I'll show you on the next slide sort of the way that I like to think about this and see this, this is all due to discretizing the continuum. And so when you do this, you're going to introduce an IR cutoff in some fashion. And so you're sort of putting the thing in a finite box. So another way to see this sort of finite box issue, or the lack of asymptotic states, is through the Lippmann-Schwinger equation. So Lippmann-Schwinger equation is just an eigenvalue equation saying h psi equals e psi, and then splitting h into h naught minus v, rearranging the equation and then inverting this down to here. So one aspect about when I now divide by E alpha minus H naught is that H naught is guaranteed, because this is a continuum theory, to have an energy eigenvalue that's the same as H. And so that means there will be some state labeled phi here, which is an eigenstate of H naught, which has the same energy. In particular, that means this matrix H naught minus E has a 0 in it. So I have to invert it. When inverting it, I have to be careful and add an I epsilon. This plus or minus I epsilon actually specifies the boundary conditions of either an incoming or an outgoing wave. But the issue with truncation is that we're using H naught and H are both finite dimensional matrices, meaning that they're going to provide discrete spectrum, and those discrete spectra will generically differ. So there's no need for an I epsilon. So again, there's no clear, or at least immediately clear, connection of the states outside of truncate, they're outputted from truncation, how they're related to asymptotic scattering states. So instead of going this picture of sort of in and out states overlap, we have another option. So what we learned in field theory is to actually compute S matrix elements from correlation functions via the LSZ procedure. So that's what I'm going to explain now. And what I want you to start getting in your mind is one of the outputs of truncation is sort of this resolution of the identity. And it's an approximate resolution of the identity because it's truncated at some value capital N. So computing the S matrix comes from essentially two basic steps. You take a correlation function, and you can evaluate a correlation function just by sticking the identity inside of it a bunch of times. And okay, so to a little more detail, from in between any two states, you can just shift O to the origin, and then these objects are easy to compute. Okay, so now we know how to evaluate correlation functions, but then you remember that LSZ tells you scattering amplitudes are related to correlation functions. So if I have the scattering amplitude and I pull out particles 2 and 3, reduce them, you have this formula. So I'm choosing to leave particles 1 and 4 on the outside here because it's sort of beneficial. It saves time. So one thing out of spec truncation is you'll get the spectrum, and you should be able to easily identify the stable bound states because they're isolated from the continuum. So we'll use that data and use them as the X, stick them in as the external states. So I'm only going to choose to reduce out 2 particles here. And so, great. All I need to do is take this correlation function and insert an identity. So those 2 objects will give me the S matrix. Now it's almost that simple, except when you think a little bit more, you're going to realize that you have a problem numerically. So of course, the amplitude is an on-shell quantity, meaning all p squareds equals m squared. And these box plus m squareds, of course, if I integrate by parts over here and act on the exponential, I get p squared minus m squared factors. So when I send on shell, these are exact zeros. And that's not a problem because the whole point is that correlation function, its residues contain the S matrix, and it's the whole setup of LSC. So this correlation function will develop poles, which then get canceled by multiplying by these zeros. The problem we have at hand is that the resolution of the identity that we have is only approximate because it only runs from 1 to n. So the poles that develop from us inserting the identity are therefore also only approximately poles. So we're taking an exact zero, p squared equals m squared, and multiplying it by an approximate pole. So this is just 0. So we need to find a way of getting around this. The solution to this is actually just to use the equations of motion. So the equations of motion tell you that box plus m squared on phi is equal to j. We're just defining j through this equation. So it's in particular for like a lambda phi to the 4th theory, it's just lambda phi cubed. And then I can literally just use these on the correlation function and bring it in. So I get 2 j's, and I'll explain why in a second that you get a contact term as well. But the whole point of this is that these objects are manifestly smooth as everything goes on shell. So you're already actually using the LSZ like truncation, amputation, that's what I'm looking for. And so now we have smooth objects numerically that will give us access to the S matrix. So how do you arrive at such a formula? Well, again, it's morally believable because I'm just using box plus m squared phi equals j, so that explains the first term, but where does the contact term arrive from? Or how do I know that this is valid non-perturbatively? One way to see it is via the Schwinger-Dyson type relation. So Schwinger-Dyson tells you that the path integral is invariant under arbitrary variations. And pulling this delta delta phi in, you get a delta s delta phi. So Schwinger-Dyson relations give you relations between delta s delta phi and other correlation functions. And the key point is that delta s delta phi contains box plus m squared acting on phi. So we can use this to trade through j. And since you have sort of a functional derivative here, you're hitting the operators and you can pick up sort of contact terms. So that's precisely what happens here. And so there's an easy way to think about this, which is that I have sort of 2 phi's and 2 box plus m squared. So I can act box plus m squared on phi and get a j. And so I can turn any phi here into a set of 3 phi's, for example. Or the 2 particles could actually interact together first and then come together. And that's the origin of the contact term. So the full amplitude sort of has this structure of what we call a JJ term and this J prime term, the contact term. And again, for a phi to the 4th type theory, J is like a phi cubed and J prime is like a phi squared. We like to call these the cat in the hat diagrams. That's why they have faces like that. Note that if the physical mass, so the actual eigenvalue that you measure out of truncation is different from the bare mass that goes into the Lagrangian, you need to add into J a term proportional to the delta mass squared as well. Right. So how do we sort of understand what's going on here? Well, the JJ term is a correlation function, meaning there's 2 J's and we can insert the identity between them. sort of like imagining cutting this diagram. So there's really physical on-shell degrees of freedom propagating. The J prime diagram is actually just a matrix element of J prime between two states. At leading order, it's just going to give you for let's say a lambda phi to the fourth theory, the lambda term. This lambda term doesn't vanish as s goes to infinity. So technically it's a subtraction term in the amplitude. So I'm going to show you on the next slide that this whole calculation is actually really a dispersive calculation the way it's set up. So second ago, we had this LSZ formula of box plus m squared acting in correlation function inside a Fourier integral. Doing the Fourier transform, we get this object in the bottom part. These first two things are part of the JJ term. They're just the two different orderings from the time ordering. One of them naturally comes with sort of an S sort of kinematics, and the other one naturally comes with a sort of T kinematics in it. Now, if you recall what a dispersion relation is for a fixed U dispersion relation, it's saying that you can construct the amplitude entirely from the imaginary part. And that's really just saying that you have these branch cuts along the complex S plane. And so I first just pick a random point in here. The contour integral around this point is 0 because there's no non-analyticity inside. And then I extend this contour as shown in the diagram. And as it goes around here, and if it vanishes at infinity, I'm literally just picking up going around this branch cut, so I get the imaginary part. Now, let's look at what the truncation calculation is doing. So this is an integral over S prime. S prime in this problem in the below will be like m alpha squared. So what we're doing with truncation is we're summing over the m squared eigenstates that we get. S is just a parameter in this calculation. And so, and these matrix elements here for scalar theory are all real. So the imaginary part of this is given just by a delta function s equals m squared. So this calculation quite literally is the above calculation. So to just summarize the recipe, it's again, you reduce out two states and use the equations of motion. You can easily read off these external states out of the data. And then we insert the identity and just compute matrix elements. Any questions?
Sorry, I think I lost it, but at some point, here you are only considering these matrix elements you can compute from the Hamiltonian truncation, right? The P4J, and then you have the states because you build them from the spectrum.
Yeah.
But the P4 is also an asymptotic state, right? So
the what?
The P4 is an asymptotic state?
Yes. But sorry, one particle states, both the in and out states can be identified and they're trivially asymptotic.
Okay. Yes.
It's just a single particle, so there's no interactions.
Okay, I understand.
Yeah. No, that's a very good question, especially considering what I was saying of no asymptotic states.
Okay, yeah.
Okay, so let's carry this recipe out. So the theory that we studied was the 2+1 ON model at large N. We picked this model because at large N, it's analytically solvable. So we have something to compare to see if we're doing things correctly. Essentially at large N, so you have this, it's basically a phi to the fourth interaction. And at large N, particle number changing processes are suppressed. So it's dominated by these sort of chains of bubble diagrams in either the S, T, or U channels. So our hope would be then to reproduce each one of these amplitudes. Where do they show up inside our calculation? Well, remember, we've chosen to reduce out particles 2 and 3, and we'll just stick to that choice for this calculation. In that choice, the S and T channels show up inside the JJ diagram, and the U channel is actually entirely a subtraction term, and shows up in the J prime. So of course, you could be smart or clever and use things like crossing symmetry and just compute one of these and then get the other by using crossing symmetry. We want to make sure the method works, so we're going to really get the U channel outside of J prime and make sure that everything is correct. Let me explain a little bit of the details which go into this if you're interested. So the whole point was to start from an H naught, which you knew, and one type of theory that we know are free theories and how to solve them. Now, that's actually already a difficult problem, but at least in terms of explicit construction. Another option would be to work around some sort of interacting fixed point, which you know the data of. Either maybe it's a perturbative fixed point, or you can use something like the CFT bootstrap to determine its spectrum. But anyways, we'll be working from free theories. So the Hilbert space is just a Fock space. Then the generic state in the Fock space is just a wave function on top of the momentum eigenstates. And so the first thing that we're doing is sort of building the H naught eigenstates. So these correspond then to, so you have some wave function on a n particle state. You need an inner product in the system. And so the inner product just amounts to integrating over the phase space of the n particles, subject to them all also being to some total momentum p. So it's just a space of square integrable functions on the phase space. So we want a basis then for this space of functions. And note that there was inside of here, importantly, a sort of delta function. So summing all the little momenta up to some total momentum capital P, that will compactify this phase space. And so whenever you have a compact phase space, compact space, you can approximate arbitrary functions on it with polynomials. So that's what we'll use. Now, another way of looking at this is it's actually precisely a partial wave decomposition. And so if you go to the two particle sector, these will be precisely the PL Legendre polynomials. At higher particle number, it's more complicated, but it's the same basic idea. Another way of viewing them is also as these are actually equivalent to being conformal primaries in the free theory. Okay. So now that we have some state set way of having states, let me explain to you what the truncation parameters that enter in. So the first truncation parameter that we'll have is polynomial degree. So the idea is that the low degree polynomials sort of cover the whole space, and higher degree cover oscillations. And so hopefully the low degree one should capture long distance physics that we're interested in. So that's the first truncation parameter. We'll only keep states up to a given degree. And then the second one comes from, and this is a little bit technical, but you have this capital P, and of course we have to sum over all those P's. And so we introduce a UV cutoff for it to compactify the space of allowed P, capital P values, which we translate into mu squared. So that's the second truncation parameter. And the very basic idea for matrix elements is that, let's again pick a pi to the fourth interaction. It's essentially can be thought of as a dagger to the fourth plus a dagger cubed a plus so forth. And so you can just use this to insert between your states and compute everything. So it's straightforward QFT calculations. Now, for the ON model at hand, we saw in the previous slides, the analytic result actually comes at large n from summing all these sort of bubble diagrams. What's happening is you're closing the loop, so you pick up a factor of n, and that's why it dominates. So that's one sort of thing that, what am I trying to say? I apologize. So the point of what's happening here is that the particle number changing processes are suppressed. So in particular, this a dagger squared a squared is the leading n term, and all these other terms in here are 1 over n suppressed relative. So we can implement the large n limit analytically in our result of just only computing certain types of matrix elements. And another consequence of this not having particle changing processes in the large N model is that single particle states are not renormalized. There should be a little asterisk here because at some points for a calculation, like in the U channel, you actually do need what would be a subleading correction here, but it gets canceled by N factor on the inside. That's a sort of subtlety. More or less, the single particle states don't get renormalized here. Okay. So the truncation setup is to have, we have these two terms coming from the JJ thing, an S sort of kinematics and a T kinematics. And the various S channel and T channel and U channel flavor amplitudes, how do they show up in here? Well, for example, let's just focus in on this S channel one. This one actually shows up in this top JJ term like this. And what you get in it by, if you cut this at any point, you just have two particle intermediate states. Whereas this diagram on the right, so the sort of vertices got swapped by, this was originally J3, J2, and now this is J2, J3. So if I cut this one, as shown here, I have a 4-particle intermediate state. So you can sort of also track what states are contributing to where through the calculation. And let's get to the results. So I already showed this plot at the beginning of the talk. And or I showed, sorry, the cross section at the beginning of the talk. This is the amplitude. So on the left is the imaginary piece of the amplitude, and on the right is the real part. You clearly see threshold behavior. So at S equals 4m squared, the imaginary part turns on. Below S equals 4m squared, the imaginary part is 0, but the real part is non-zero. Just think of lambda applied to the fourth, the leading term in the amplitude is lambda, the real part. Also, just as some other, just make sure you're doing the right thing at high energies. This theory becomes free because it was a relevant deformation. So the leading term in the amplitude should just be the perturbative lambda. It's constant, so you're seeing it head towards that. You can see that this also has the leading behavior of a 1 over S as you get to larger S. The really important thing or interesting thing here is that the residuals on these, so these are about percent level accuracy that we're getting over a large range of energies. And I'm pointing out here, so the residuals, as soon as you're actually hitting physical states, that's when you get a little bit noise in the data. But as soon as you leave the physical region, everything's super smooth. We get very good convergence outside. So as you can see here, let's show that in a little bit more detail. So this plot here is a plot of the residuals on the absolute value of the amplitude. And one thing about it is we can calculate this whole thing in the complex plane. The way to read this plot is that the different colors are order of magnitude of how accurate the calculation is. So outside in here, green, we're having per mil or per 10,000 sort of accuracy. And it's noisiest and least accurate, but again, it's still order 1% accurate along the real line. One thing about this is we're in the complex S plane. So that's represents a very interesting object to study. If you're, in terms of convergence that we were just mentioning, it could be plausible to actually, since we have very good convergence here, to fit a function out here and analytically continue in. But at the moment, our numbers, our numerics are already quite good, so we're happy with it, but it's a thought to have for future applications. This is a repeat of the previous plot on the left, and on the right is the phase of the amplitude, the residuals for that. So again, we have this rapid convergence throughout the entire complex plane.
Why isn't there clearly the crossing symmetry? Why is not there like the T channel and U channel?
So the ON amplitude, at large N, it really factorizes into an amplitude that's really only a function of S
Okay.
for the S channel. And so it doesn't actually pick up that cut. Good question. All right. Other questions?
When you say you only use a laptop, is how powerful is it? Like how long does it take?
A few seconds on a standard laptop that a PhD student can afford. So now
It's incredible.
yeah, I mean, there should, I mean, some things though, just to know, I mean, the numerics are quite great and fast for the ON model because of this sort of factorization of, or no particle changing processes. You sort of know most of this was set inside sort of a 2-particle sector, that's sort of the states getting exchanged are 2 particles. And so there is a little bit of like, we didn't have to go to very high particle number and building the basis. And sometimes that's where time gets costly in other truncation calculations. But in general, yeah, this was done in like less than 10 seconds, the calculation. So future directions. So the being able to access information in the complex plane, I think, is one of the most interesting questions coming out of this. So the complex plane, its non-analytic features tell us a lot about physics. So for example, below threshold, you might have bound states appearing. Now those should be easily readable outside the spectrum or from the spectrum output of truncation. So that's a mystery that's already solved. But what about something like a resonance? So near a resonance, you get a pole and a pole on the second sheet and a 0 on the first sheet. So can you see this sort of information? It manifests along the real line, like in an experiment, as a bright Wigner distribution. So there's no doubt that we will see sort of a bright Wigner distribution, but the question is, can we somehow measure a pole or a 0 of the amplitude, and how good is the convergence there? I want to point out that for the setup that we are using of just sort of reducing out 2 particles, this gave us enough freedom to allow arbitrary S, but it's still for fixed U. If you want to study arbitrary S and T, so allowing both of them to be complex, you need to allow more particles to go off shell. So like initially, so such as the 4-point interaction. So maybe it's worth taking a look at this object. A puzzle about the analytic structure, and one that I think will be very interesting in trying to study, is can you really access any of the multi-sheeted structure of an amplitude? So in the continuum, we know that there are sort of branch cuts arising at thresholds. And as I pass through those branch cuts, I enter on to higher Riemann sheets of the amplitude. But what truncation gives you is actually a dense set of poles along the axis. Of course, a branch cut in a sense is an integral of a dense set of poles. But so we only have the discrete set. So to what degree do we actually be able to see interesting features that lie outside of the physical sheet? The part of the fourth theory that we looked at in this talk, it's a repulsive interaction. So there are no bound states in the system at low energies. This was sort of manifests itself from the fact that we could actually use phi, the original field, to interpolate the single particle state. So when the LSZ procedure tells you that I just need any operator O, which interpolates the single particle state. And this I can use inside the LSZ procedure. That's why there should be a factor of 1 over square root of Z. And bound states, which are generally meaning composite states, they will require generically a composite operator for their interpolation, such as for pions, you can use either Q bar gamma 5Q as sort of the leading operator, or the axial currents or things like this. That if you recall, the issue is that this box plus m squared contributes a 0 that's supposed to cancel against a pole inside of here. And we got around that by using box plus m squared acting inside here. And when you know the fundamental field, if it's that interpolates it like phi, we can use box plus m squared equals j. But what happens and how do we generalize that to a case when we have composite operators? This is an important thing to figure out at the moment. It's completely necessary if you want to study a theory like QCD. Some thoughts we have along the way of maybe you can use Ward identities if you're studying objects interpolated by conserved currents, or such as axial currents or the stress tensor. Maybe you can literally just let box plus m squared go through and act on the constituent fields. This is, and there are some other ideas that we have, but this is an important thing to figure out. In terms of like what truncation or what theories would you maybe want to study as well? Of course, we showed you work in 2+1 dimensions, which was important for us because we really want to be working towards the real world. But in 2 dimensions, there's a lot of very interesting physics and analytically solvable physics to compare against. And so it's worthwhile to implement the procedure in 1+1. But I think what really excites me is extending towards more realistic theories. And I'll talk about gauge theories in a second, but some things that you might want to think about, like from earlier on in the talk, is that there's this Pomeron and forward physics. And so is there some way of studying strongly coupled forward physics through either like a phi cubed theory in d = 3 or something like this? Now, the object or the theory that we all want to actually study is gauge theories in 3 and 4 dimensions in QCD. So at the moment, the existing technology for truncation can handle scalars and fermions in arbitrary dimension, but only gauge theories in 2D, and that's because the gauge field is non-dynamical and you can integrate it out. So there's no inherent reason why it can't do it. It's just that this is a small community that hasn't been working on it. And so I think it's very important that we start on this important goal. There's a couple options available, which is excuse me. Sorry. A couple options about what you might want to do. So if you want to study a gauge theory, what is being done is you're turning on, let's say, G, A mu, J mu coupling. The problem with this is that that's not a gauge invariant deformation. And so it hasn't been figured out yet what sort of gauge fixing procedure needs to go on to study this directly in sort of the naive way. Another option, one that I think is very interesting, is to actually start from an interacting fixed point. So if you take like Banks-Zaks with, let's say, 16 fermions in it, it's a perturbative conformal theory. Or I could take n = 4 super Yang-Mills and imagine using some sort of integrability and bootstrap combination to measure the spectrum of that. And then I can add as my potential just mass terms for all the particles that we don't want. So in Banks-Zaks for the 13 other quarks that we want to get rid of to get to QCD. And this is a well-posed problem from a truncation viewpoint because this is a gauge invariant deformation. Moreover, it's a relevant deformation. So I think that this is a very interesting avenue to pursue. I think QED3 represents a very good target for the sort of first, why don't we go through the sort of gauge fixing procedure? There's a lot of interesting physics there and it should be easier in an abelian case. There's actually a ton to be doing with truncation, plenty of projects. And so if anyone's interested, I'd be very happy to talk to them. But thank you. And I just want to thank my collaborators as well. And again, point out Jed, who's a superstar. Thank you so much.
Okay, very good. Thank you, Brian, for the very nice talk. Thank Brian altogether. Okay, let me give the opportunity for questions. Any questions? Neither at home, I suppose. Okay, if not, let's thank Brian for this wonderful talk.
Thank you. Thank you for having me.
Okay, very good, Brian. Thank you. Thank you once again.